So our next speaker, I believe, is in your group, Nathalie Nießer, also from the University of Bundeswehr. Welcome, Nathalie. Nathalie is going to be talking about the different failure scenarios of load-bearing glass structures, and she's looking into the matter in both lab tests and simulations. It's her first time presenting, so give her a very warm applause and encourage her. Good luck.
Thank you. So, thank you for having me and joining my presentation about the development of a safety concept for the assessment of different failure scenarios on load-bearing glass structures, where I'm going to present some of my research about the development of a hybrid digital twin for critical infrastructure like glass facades. So to start my presentation, I want to show you a short analysis of structural damages conducted by the Institute for Building Research in Germany, which took place between 2016 to 2020 and had a total of almost 50,000 damages in the building construction sector. And what you can clearly see from this graph is that the most frequent damages are to facades and windows, with almost up to 43%. And this can have many reasons for this high rate, but the most probable is that nowadays facades are highly technical building components, so they are among the most complex and demanding building components in terms of building physics. So the planning of facades is really complicated by the handling of their tolerances, because there are different tolerance ranges depending on the material. So if there are different materials used in a glass facade, there are also different material-related tolerances that have to be taken into account. So there are many uncertainties. And one of the main problems is the sudden failure of individual glass panes, which can have a significant impact on the safety of the entire structure. But if there would be the possibility to detect an error in a facade at an early stage, this can have an influence on the further course of the whole project and, of course, on the development of the damage itself. So, for example, by detecting a damage at a really early stage, there only would be a small area in a facade to replace, or even serial defects could be avoided. So, to achieve this, some changes need to be made, or respectively, necessary action for this could be, for example, to develop new concepts for communication and planning structures during the construction, and also the ability to forecast incidents or failure scenarios have to be improved. And especially for the last point, the ability to forecast incidents, a digital twin can be really useful for damage prediction. So that's why I want to explain what I mean by saying a digital twin. So to create a digital twin, we are starting to collect various information about a building. So, for example, digital planning documents like CAD or BMI documents, or also digital building surveillance by drone images or laser scans. And also informations are collected due to sensor data, for example, by installing humidity, temperature, or deformation sensors for a long period on a building. So the sum of all this data is then collected into a digital twin. So we can use this, for example, for optimizations on the planning process, or for operating costs, or for the identification of changes by comparison with our so-created model, like for simulation of different damage scenarios. And the digital twin also can be used during damage events, for example, by modeling the damaged structure. So the main question we are facing now for the development of our digital twin is how we can defect, or how can a defect in a facade be detected in an early stage, so in order to contribute to damage minimalization or even to damage prevention. So our goal is to create simulatable and also data-supported virtual images of real existing structures by doing detailed recording of the building behavior, and also doing simulation of failure cases or failure scenarios. So our task is first of all to design a model of the construction as close to the reality as possible, and also doing sensor measurements on the real existing objects so that we can combine everything to a digital twin. So in order to address this digital twin also to glass facade constructions and improve the safety of these kind of structures, our aim is to develop an improved safety concept. Which means, for example, we are examining a building structure made of wood and stiffening glazing that, for example, can be seen here in the picture. So basically, the stiffening steel frames are replaced by our stiffening glazings here, so that the panes are designed in such a way that in the attic or in the ground floor, each pane can take up the full stiffening load. So we can use this model for simulation of the failure of one or more glass panes in order to determine the effects of the damage on the overall structure in general. So, like I said, in addition, we also need real-life test facilities because they are also required for our digital twin. So for this purpose, a sensor system or the sensor technology must be planned to record impacts like temperature, humidity or wind, and the effects like deflection and stresses on a facade. So that we can have a comparison of our numerical model and the measured reality like geometry or effects due to our impacts. And we are primarily doing this monitoring on glass facades. So we are also installing our sensors directly in the facades. Like, for example, installing sensors in the glazing, or using facade test stands, or even doing examinations on real existing buildings, so that we finally create a database for simulation. So to assess now the damage on glass facades, first of all, we have to create a numerical model of our structure. So, for example, here's a picture of a model which consists of 4 stiffening glazings. So we use this for our simulation to determine the effect on the overall structure by damage in general. So we can first of all make quantitatively determination on the influence of various loading scenarios. So, for example, here is a variant of if only one glazing would fail, and how this would affect the load redistribution to the undamaged panes in the system in percentage terms. So, for example, what we now can here analyze is that the impact on the third pane, or if the fourth pane is failing, then, for example, the third pane has a greater impact in order to, or than it would have if any other pane would fail. So we are using this information for investigation of the impact so that we can use this for further risk analysis. So the next step is that we are mapping the different failure scenarios on a so-called event tree, so that we can now make to our quantitative statement also qualitative statements about the failure. So therefore, the failure of one or more glass pane is examined for the probability of occurrence and the extent of the expected damage. So there, the discussion of the acceptance of a consequence starts. So, for example, if all 4 panes would fail, the consequences are very high, so there could be a risk of collapse or risk of injury, so that the percentage of this risk has to be lowered than, for example, some consequences who are not that bad, like aesthetic impairment or energy loss. So the event tree only focuses on the consequences, but we also have to analyze the causes which can lead to a damage or an impact on such supporting structures. So, for example, the causes of damages in building constructions can also be seen here in the graph. So several independent reasons for impacts can be now integrated in our graphic. So, for example, execution or assembly errors, or weather influences, as well as wrong static calculations or construction or wrong construction supervisions, and also like external influences, even if they are really low. So all this can be now included in our diagram. So regardless to the causes, the consequences can now also be examined again. So if a pane is damaged, we can now decide even if the damage is now detected, like are there sufficient measurements are taken. And these can only work if there's alarm system, and also the organization of damage repair have to succeed. Only then we have a sufficient, only then we can take sufficient measures. If maybe so then we would have no damage because of our early detection. If this won't be the case for some reason, then we have maybe a failure in our supporting structure, even due to our warning system. And there can also be the case that the damage is not detected. In this case, we need sufficient redundancies, so that we don't have a damage. If there aren't these redundancies, then the support structure can also fail without a warning. So based on these results, qualitative statements can be made about the maximum credible damage. And as I already said on the event tree, we can also now analyze the risk and categorize them. For example, when we have a failure in a supporting structure without a warning, the consequences are really high. If we now have an impact on a supporting structure and we recognize this due to our alarm system, so this is a really low consequence. So that's why the percentage of the risk is here now higher. And this is actual, what I'm here showing is only a small example of the impacts that influences the failure, what can happen. So it's, when it's getting bigger, it's really hard to understand. So a digital twin can be here really useful for collecting this data, and also evaluate and capture these relationships. So for example, here we could say, if we improve our alarm system or investigate the redundancies, our consequences could be changed to something more positive, for example. And as I said, we also need this alarming system by installing sensors on real existing structures. So for example, we are planning here a sensor concept for a glazed roof. Since the damage on this building is already visible, the sensors can here also be attached specifically on damaged areas. So we decide here for sensors like pressure sensors, weather stations, thermowire, or also humidity sensors. So the aim is to capture as many influences as possible. So in the end, our virtual building model of stiffening glazings and the real existing test facilities should lead to the creation of our so-called digital twin. So yes, the examination of redundancies in our digital model and the real-life building can be then examined by sensor technology. So we can make a more precise prediction of the deformation of glass facades, and also to evaluate structural damage and analyzing patterns. So we have a more precise prediction of the allowable damage on glass facades. So to sum up my presentation, nowadays facades are highly technical building components. So they are among the most complex and demanding building parts in terms of their physics. So one of the main problems is the sudden failure of individual parts of this facade, which can have a significant impact on the safety of the entire structure. So the goal is that the ability to predict incidents or failure scenarios for facades need to be improved. So our goal is to create, first of all, simulation capable and data supported virtual images of real existing structures like on our facade, so that we have a detailed recording of the buildings, of the behavior of the building. So we can also simulate our damage cases or our damage scenarios. So therefore our task is first of all doing simulation of the failure of our glass structure in order to determine the effect on the overall structure in general, so that we have quantitative statements about the impact. And these are then combined with our event tree analysis and cause and consequences diagrams, so that we also have qualitative statements. So therefore, we need sensor technology to record impacts like temperature, humidity, and wind, and also effects like deflection or stresses. So that we have so that we can compare our numerical model and the measured reality, like the geometry or the effects due to impacts. So we have a more precise assessment of the load bearing capacity of and safety of our glass facades. So here are some references, and thank you very much for listening. So if there are any questions, please ask.